Hey everybody, this is Mr. Munson. This is Reducing Radicals. Now some of you might be good at this, but my experience is in a regular geometry class like this, reducing radicals, working with square roots and things like that is quite troublesome for most of the students. So let's make sure that we have an understanding of how to basically work with these things as we go through, especially unit number or unit number 7. Uh, um, right triangles. So let's make sure you understand the vocabulary. Perfect square. Perfect square is just basically something that when I give it to you like this, square root of 4 is 2. Okay, so what turns out is 4 is an example of a perfect square. 9 is a perfect square. 16 is a perfect square. Um, 36 is a perfect square. 25 is a perfect square. Basically, these are numbers that have been something squared to get there. Okay? Right? So 2 is not a perfect square. 3 is not a perfect square. In this case, 4 is a perfect square, but 4 squared creates 16. 6 is not a perfect square. 5 is not a perfect square. But when we take a look at these numbers, when we take the square root of those numbers, we can pretty much do this in our head. 7 is not a perfect square because when I take the square root of 7, um, in my mind, I'm like, what do I multiply times itself to get 7? Nothing I can think of. And if I did that on my calculator, I'd find out it's probably around 3.6 or something like that. Okay, so when I take the square root of a number and it turns out to be a decimal or something like that, it's not a perfect square. All right, radicals. Radicals are just things in this form. 3, you know, and this can be a radical too. I put a little 3 out here and 27, and so that's saying the cube root. Now we're not going to deal with that in this year right now, but those are called radicals. Denominator. Just remember the denominator is the bottom. Okay. All right. So make sure you understand those basic vocabulary words. Let's take a look at reducing these things. So these are the basic rules for dealing with radicals. Make sure you combine like radicals. Rules of fractions, simplifying, all that stuff, that all applies when we're dealing with radicals. No perfect squares left under the radical symbol. No radical symbols in the denominator. And radicals are written last, okay? All right, let's make sure we understand what those concepts. So here's some problems, combine like radicals. You can always put me on pause, give yourself a chance to figure it out on your own, see if you understand it, and then come back and check your work. That's the preferred way. If you have to sit back and watch this video and just watch me do it, you're going to get some learning, but nowhere near the learning that you really deserve for yourself. This is your job. This is your education. So let's make sure you know how to do this, okay? So I'm going to show the work on doing each one of these. I'm going to pause right now for those people who put it on pause and try to figure it out on their own. That's a brilliant way to see if you do or don't know how to do this. All right, that was simple enough. That's no radicals in that at all. That's basically algebra 1. I like to underline like terms, and so I'm going to do that same thing with this next one with radicals. So put me on pause, see if you can figure this out on your own, and then let's come back to it. And there's what we get. Okay, so we have 3 square roots of 7 sitting someplace. We have 4 sitting in another place, but when we add them together, we get 7 of those things. Now, just so you know, the 7 on the outside can't be in any way manipulated with the number on the inside. There is a way of doing that, but it's later on in algebra that you deal with that. But that 7 is on the outside. I like to think about the numbers underneath the radical as being kind of in prison. And you can't play with the prisoners unless you're inside prison. 7 is outside the prison. So hopefully you got that answer there. Let's move on. All right, rules of fractions apply. So let's take a look at reducing this. Make sure you know how to reduce this thing, okay? I'm going to do this. You can put it on pause or just simply watch me. Okay, but you know, a lot of times students, hopefully not you, but sometimes students reduce one time and they think they're done. But actually 15 over 21 still has another factor that can be factored out. Hopefully you've gone on and come up with that. I'm going to do that work right now. All right, and there's no more factors. Now, one of the things the reason I did this problem without any radicals in is I wanted to show you that I put the like terms right up front so they cancel each other out. I kind of intentionally did that. I'm going to kind of keep that same thing going when I'm looking at reducing fractions and doing radical stuff in general. Okay. All right, so let's go down to example number 4. Now we're looking at example number 4 and reducing that. So see if you can do this one on your own. All right, there we got it. Now we're not breaking any rules. We don't have any other radicals to combine together. So let's move on to the next. You can put me on pause and see if you can do this one on your own. There's no factors of 3 to be broken out. There's no simplification of square root of 5. So there's no factors, common factors between the 3 and the 8 to cancel out, but the square roots of 5s do cancel out. They're factors of each other, right? So this ends up being 3/8. All right, easy enough. Square root of 16, I hope that you know that one to be 4. Now let's try to reduce square root of 63. So let's do this one together, okay? So what I'm going to do is I'm going to set up 2 radicals, okay? And I'm looking here, and put this in your notes so that you have it as a model, right? Perfect squares, okay? So we've already defined what perfect squares are. I'm looking for a number that goes into 63 that if I took the square root of it, I could do it in my head, right? Well, I know 9 is a perfect square that goes into 63. So I put it up front, and then I put the other number. So I know that the square root of 9 times the square root of 7 give me the square root of 63. So I just kind of busted it up, okay? Putting the perfect square first. So now I'll simplify this. The square root of 9 is a complicated way of saying 3 square root of 7. Now if I wanted to see if I did this right, I would take the square root of 63, and when I do that, I get the number that's approximately equal to 7.937, so on, okay? So then I take this 3 times the square root of 7, the final result that I got, and I get, whoops, I did that wrong, 3 times the square root of 7, and I get approximately 7.937, so on, same number. That tells me that I've done my work correctly. If I took this number and plugged it in my calculator and took this number and plugged in my calculator, got 2 different numbers, I've done some kind of simplification error, okay? All right, so go ahead and put me on pause and see if you can do the square root of 180. Look for perfect squares. All right, and there you have it. I did square root of 9 times 20 gives me 180. Square root of 9 is a complicated way of saying 3, so there it is. Now, when I got to this step here, I looked at the 20, made sure that there was no more perfect squares underneath the radical. Just like when I'm dealing with fractions, I make sure there's no factors that are still remaining. Even though I reduced once, I could still possibly reduce over and over again. And so, in fact, 20 does have a perfect square. It's number 4. So I write 3 numbers. The 3, I bring it down. Square root of 4 times square root of 5 gives me square root of 20. So the square root of 4, as I show, gets canceled out and turned into a 2. And so it ends up being 3 times 2 is 6. And that leaves me that square root of 5. Now some of you might have taken the square root of 180 and realized that there was a nice big 36 that divided into that. Okay? So if you take 36 and divide it into 180, you get square root of 5 times square root of 6, okay? So square root of 36 times square root of 5 gives me 180. The benefit of that is we know square root of 36. We know the 36 underneath the radical there is a perfect square. So I can just jump right to the answer, okay? So I sometimes try to look for the biggest possible perfect square that goes into a number, but when you're starting off like this, it's probably safer and easier for you to just kind of look for the little bits, the smaller numbers that go into it, okay? Let's try the go on to the next stuff. So here's the thing. It says no radical symbols in the denominator. So I have to go back and kind of cover something that you already know. 3 times what number gives me 3? So hopefully you said 1, right? 3 times 1 gives me 3. Now I'm thinking of another, look at the 4 one there. I'm thinking of a number that I multiply times 4 and I get 4. See if you can guess what number it is. Put me on pause if you need to, and then come back. I bet you none of you thought of that number, but that really is the number 1. Does everybody agree with that? That 1050 divided by 1050 is the number 1. And the reason I say that 4 times that is still 1 is that what we find is 4 times any type of 1, right? And this is what I call my special 1. Okay, it's a special 1. It just, it's some random number over the same number, and that will result in 4 being the case. Now, at first, when I multiply it, it won't look like 4 anymore, but once I reduce it down, it turns back into 4, because 4 times 1, and in this case a special 1, still equals 4. You have to understand that. Go back and listen to that again if it doesn't make sense for us to get into the next exercise. Okay, so let's look at example number 9. So in example number 9, it's breaking the rule. There's a radical in the denominator. So what I'm going to do is I'm going to multiply the denominator by square root of 5, because this is what I know. Square root of 5 times the square root of 5 equals the square root of 25. And the square root of 25, well, 25 is now a perfect square. The square root of 25 is 5. So I break it out of the radical. But this is really important. I can't take a number like this and just multiply it times any number and keep the same value. I have to multiply it times a 1. Some number times 1 is the same. Now I might change the look of it, but it's still the same value. So what I have to do is multiply it by my special 1. Okay? The special 1 is the denominator's radical over the denominator's radical. Okay? So this is my special 1. So what ends up happening is I get this 3 times the square root of 5 over, the square root of 25. And this all reduces down to 3 square roots of 5 over 5. Okay? Now, the 5 that's on the bottom cannot play with the 5 on the top because the 5 is in the prison on top. Okay? But what I would want to do is look at these numbers, make sure there's no reduction that can happen. Is there a factor of 3 and a 5 that can be canceled out, just like any fraction? Okay? In this case, that doesn't happen. All right, so take a look at number 10 and see if you can do number 10 on your own. Put me on pause. So I'm hoping that you said, you're going to multiply by your special 1, right? Okay, so then I end up with 3 square root of 2 square root of 5 all over 5. Okay? Now the top has multiple radicals, so I'm going to combine those radicals. So square root of 2 times square root of 5 is the square root of 10 all over 5. So let's just quickly make sure we're not breaking any rules. There's no radical in the denominator. There's no reduction in the fraction that needs to happen. The 5 cannot play with the 10. Otherwise, we would try to reduce that. Can't play with the 10 because the 10's in the prison. Okay? All right, there you go. All right. Last but not least, the radical is written last. Okay, so if you look at this, I have a series of numbers here being multiplied. There's really 3 numbers here that are being multiplied. We have the square root of 5, we have 3, and we have the square root of 7, all being multiplied because there's parentheses or a number right next to a radical. It's all 3 numbers being multiplied. Now, if I'm multiplying numbers, I can multiply them in any order I want. So the 3 is outside the radical, so it can't play with the radicals inside. The things in the prison, but the square root of 5 and the square root of 7, those things are actually both in prison, so I can actually put those things together and call it 3 square roots of 35. Okay? Now once that happens, I want to start asking myself, is there any perfect squares that can go into that square root of 35? Is there anything that can be factored out? Okay? In this case, no, there's nothing else left inside. Okay? All right, let's look at example number 12. Feel free to put me on pause and see if you can put those things together and simplify it. All right, so I have 15 plus 2 square roots of 5, right? So easy enough, the 3 and the 12 go together to give me 15. And then the 4 square roots of 5 minus 2 square roots of 5, those square roots of 5 being similar, I can take those things and put them together and I get 2 square roots of 5, okay? Now remember, this is the case where I'm adding, this is the case where I'm multiplying. When we're multiplying, we took the square root of 5 and the 7 and put them together. But in adding, remember, you can only add like terms. Refer back to one of the very first examples that we did to see how you can't take certain square roots and put them together because they're not the same ones. Okay, that's it. Let's take a look at